All right, where are we at, Justin?
You got 70.
4370?
73.
73. Oh, I like that. This one's neat. It's kind of problem I would love, of course. So this one says, find a function of the form, it's a cubic function, where there's a max at negative 2, 3? Yeah, and a min at 1, 0. All right, this is number 7343. That problem, right? Okay. So this stage of the game, if I tell you they gave you the function, you should say, yes, they did. They gave me the function. There it is, right there. Some stuff we don't know in there, but big deal. How do I, if they give me a function, how do I find its max and min? What do I do first to find the maxes and mins? Take the derivative. I love it. So take this guy's derivative. See, what you're going to do is, you're going to start the process off, because you have a function to work with. There's just a lot of shit I don't know about it. I actually know the end. I know this. So I want to connect those two. I want to start to work with this, and then match it up with what the answers are. Right? It always feels a little bit like cheating, but I know the end, I know the beginning, I want to meet them in the middle so I can figure out what A, B, C, and D are. So what is the derivative of this? This is nice. It's just a big old polynomial.
3ax squared plus 2bx plus c.
This is where it's going to get kind of fun. Yeah, I don't think that. Now watch. How many extrema does this have? 2. Let's get 2 extrema. And the extrema would be related to, well, if there's an extreme value of a function, what is true at that point? Slope is 0. I love it. Doesn't work the other way around, right? If the slope is 0, you're not guaranteed an extreme value. That's just the where it might happen. But if there's an extreme value, the slope is 0 or undefined. I have a nice function, so I'm just going to consider the fact that it must be 0. So the derivative has to be 0 at what 2 places? Yeah, at x equal negative 2 and x equal to 1. I like it. So okay, what does that do for me? All right, so what must f prime of negative 2, what is that? That would be 4 times 3, 12a, negative 4b, plus c has to equal 0. And f prime of 1, so that is 3a plus 2b plus c has to be 0. All right, let me stop. You guys see, that's what I mean. Do you guys see what felt weird? Because we connected the answer to what we normally would have done. We normally would have taken the derivative, set it equal to 0, and solved for x. But now I set it equal to 0, and I know what x is. Now, of course, what's still kind of bad about these? 3. Yeah. So what's the last? All right. I've done enough for this one. Is that enough to get started at least? There is a problem right now that I need to let you guys try to figure out is how do I keep going with this? Do they give me any more information? No. But that should get you started. I mean, that's the big first step. So again, that was number 73 and 43. You should probably pay really, really close attention. Always pay attention, but pay really, really close attention when I say, oh man, I like this kind of problem. Which is what I said at the beginning. The idea doesn't care what's happening, right? The max and min would happen where this derivative is 0 or undefined. I have a nice function, so it could only happen where it's 0. And I know where that location is. So that's exactly what these capture, the idea of the slope is 0 at the extremes. Some of you guys might realize what the other information I have is. You have this information here. Right? Anyway, now I've said too much. That's plenty. It's too much. How many things do I not know overall? Overall, how many things do I not know? 4. 4 things. Right? So how many equations do I need? 4. Yeah, there you go. So there's 2. There's 2 more things I didn't do yet. All right, maybe. Is everybody cool with what's happened so far in this problem? Tell me if you're not. It's fine if you're not. It just sucks if you don't say anything. That's bad. Okay, all right. Anything else from homework? You had 4 things, right? No?
3, 7, 9, 85. The last 3 problems. This one.
Oh, yeah, okay. Ooh, this one's really freaky. Sorry. Justin's like, yeah, I know, man, I lived it. All right. Sure. This problem is one of my favorites. So inflection points. Show that the inflection points of y equals x sine x lie on the curve y squared times x squared is 4 equals 4x squared. I like it. When you get a problem like this, what's the freakiest part of this problem? What's the freakiest part? No. Sorry. That shouldn't be freaky, right? You're like, oh, thank God it's sine and not cosecant of tangent of natural log. You know, it's just sine. It's a product. No big deal. Inflection points, not a freaky part. I know how to find inflection points. You know how to find inflection points. The freaky part is they're supposed to do this. So when you're not sure what to do, you start working on a part that makes sense. How do you find inflection points of this? Take how many derivatives? 2. Because inflection points come from the critical points of the second derivative. There you go. Now, what gets interesting is the reason, let me just go a little bit further, because once you do that step, you'll start to realize something interesting. Help me out. What is the first derivative of this?
Sine of x plus x cosine of x.
Sweet. Good old product rule that nobody should mess up on. And what's the second derivative going to be?
Negative cosine, or no? No.
Cosine x
Cosine x
plus
or
cosine x
minus x sine of x.
Because the derivative of cosine is negative sine. So I get 2 cosine x minus x sine x. Do this now. What are the critical points of this? What do I do?
Take the derivative of
Where are the 2 places critical points come from? I don't care what level derivative I'm working with. Where the derivative is 0 or where the derivative is Undefined. Is this going to be undefined anywhere? No, cosine, sine, everything in here is defined everywhere. So I only have to consider where this thing equals 0. Are you guys? So what the shit? Why did I do? Why am I not caring about this? Bless you. Because I got to get these before I can show they do this. I mean, that's why I don't give a shit about this at first. This is really just find the inflection points of this. Now, what's weird involving trig functions when you set them equal to 0 is there could be an infinite number of places where they're. Could be. Also, if you go to solve this, this is where it gets freaky. This is why I want to go a little bit further. Solve what? What exactly am I doing next here? What did we just say I want to look for where this thing is? 0. So that would mean 2 cosine. Can I just jump to this? It's all right. So that equal to 0. You can either divide by sine. You get 2 cotangent x equals x. Can you solve that? Can you solve that by hand? Probably the way I'm asking it, the answer is no. In fact, the answer is shit, no. So that's the purpose of this problem. This problem would have been easy as shit. If I could have just got the inflection points and showed they worked in here, I'm done. It can't be that. Do you guys see that? If I would have found the inflection points, plug them in, show it works, I'm done. Here, let me get the inflection. Aw, shit. I can't solve this damn thing. Okay. So now you got to figure out, okay, what can I get from this that will help me with this? That's as far as it goes. And then what was the last one? This is where I love people that are like, he doesn't finish anything. That's your work. I did a lot of work for you. That's your work. Yeah. What was the last one? I'm sorry. Wasn't there one more? 85. Oh, okay, sorry. So this is a two-parter. Show that a cubic function always has one point of inflection. Just that first sentence by itself, right? Because the rest of it is something else. So how in the world would you show that a cubic function always has just one point of inflection? If you think about it, it makes sense, right? Here's the basic cube, right? For you guys, it'd be this. And it's got cup down, and then it's cup up. So that's one point of inflection. But this says always, no matter what the hell's going on. So what function am I working with? Yes, the general cubic function, which is? This is the general cubic function. This is talking about inflection points. So I'm not going to stop here, of course. I'm going to go to the second derivative. So that first sentence, that first part of this is not difficult. You guys are like, you're talking about for yourself, Jeff? But you take, so it's talking about inflection points. I know that means go to the second derivative. So what's really kind of funny is, if they don't really give you a function, they just say a cubic function, and you write that. You can still work with it. Your brain is going, what the hell's A, B, C? And you're like, I don't care. I got something to work with. Let me work with it as far as I can. Take its second derivative. Set it equal to 0. See what happens. You're supposed to only get one inflection point. So you just work it. Just show that's true. And then the second part's the really freaky part. So what would somebody... So not just this. This is x cubed. But what if I just let A, B, C, and D be whatever? What's the general look of a cubic? You guys should know this coming out of pre-calc. It's got how many? It's got a hill and a valley, right? That's really, or it might be, reflected, depending on who's negative. These could be big or small hills and valleys, whatever the shit. But it basically looks like this. So what's the most x-intercepts you could have? which relates to the fundamental theorem of algebra. It has at most 3 answers. Some of them could be complex. So the most real it could have is 3. So what they're saying is, if it has these 3 x-intercepts, x1, x2, x3, show that the x-coordinate of the inflection point, where's the inflection point on this? It looks to be like right there or something. So show that the x-coordinate, so that's cup down and then this is cup up. Is that cool? Show that the x-coordinate of the inflection point is x1 plus x2 plus x3 divided by, is it 3? I always forget. Yep. I know. And this is the problem that you guys have, it's such a weird dichotomy here. You like on your back about, I should know how to do, or like, I should be able to do this in 3. No. You take a whole page at least, if not a page in the back, and play with it. Just play with it. I mean, at this stage of the game, you should be comfortable with just doing shit. Well, that didn't work. Let me try something else. I mean, that's a part of the process. And I think that you guys, for some reason, you believe, well, that didn't work. I don't know. Okay, next problem. So that's weird. How the hell do I get here? Well, don't think about this. Think about what this is supposed to represent. It's supposed to represent the location of the inflection point. How do I get the inflection point? Oh yeah, I get the second derivative of this thing. Do all that. Get it first before you start to connect everything. Now what's true? Here, just to make sure. What's true about these points? If I plug an x1 in, what happens? I get 0. If I plug an x2 in, I get 0. I plug an x3 in, I get 0, right? Maybe there's a connection. Because you want the, all right, that's all I'm going to say about it. Because I have this weird feeling most of you guys haven't tried this problem yet. Or you looked at it and said, no, I'm not even going to write the problem number down. Maybe he'll miss that I didn't do it. I love that one. It works sometimes. I'm a human being, but somebody actually said that the first day. They're like, yeah, I heard from people that you sometimes miss it when I'm just going to do that. I'm like, I'm going to look at yours like insanely close, dude. You just screwed yourself over. Okay. Anything else from homework stuff? I mean, those were freaky ass end of the thing problems. Those are not the nuts and bolts. So if you're having trouble in those, that's okay. Just don't give up on them. Play around with them. Nothing else from anything? Okay, so last time, now that I got a few more people here, anybody else need the handout from last time? Everybody's got that handout from last time? Because we've got to still do the one on the back. We did the one on the front. Hey, all right. So, a real quick review, which I shouldn't do because if you missed last time, you should have watched the video by now. But, what is the, if I have a function and I take the first derivative, I get the critical points by doing what? We've already talked about this, you guys. Looking to see where, where the f prime is 0. Or f prime is undefined. And the critical points of the first derivative are where what might happen? Maxes and mins. The local maxes and mins, right? So these are locations of possible local extrema. So the number of local extrema is always at most equal to the number of critical points. Some critical points could be like, no, so some of them are going to be little assholes like that saying, nope. So sometimes you'll have less extreme than you do critical points because some of them just don't test out. Now, what's the second derivative tell me? Well, the first derivative tells me increasing, decreasing. It tells me, of course, slope stuff. What does the second derivative itself tell me about a function? Concavity. I love it. So cup up, cup down, right? Concavity. Cup up and cup down. Happy and sad. So, of course, the critical points for the second derivative, I still do it the same way. Where is this 0 or where is this undefined? And in both of these situations, I make my little sign diagram, put my critical points on there, investigate around here to see where it's increasing, decreasing, or where it is cup up, cup down, to see if there's inflection points, to see if there's... So what's an inflection point? That is where what happens? Concavity changes. Like a max or min is where slope changes. From down to up or up to down. Inflection point is where second derivative changes, right? From positive, negative, so concavity, where concavity changes. That's why it makes sense on the one problem we did. Every cubic has exactly one inflection point. There's cup down, there's cup up. Hey, that's not a proof, but that's definitely a really strong evidence that that's true. Okay, so everybody should have one of these now. I want you to work on the back. Is that true? Everybody has this handout? So work on the back of this. Please, dear God, feel free to work with other people. Call me over if you need some help. Let's just make sure, I'm really kind of concerned. So here is the function I'm dealing with. What's wrong with the form of it?
It's in square roots.
Yeah, radical form of it, right? And I don't know if you agree with me or not, but radical forms should not exist. We almost always have to change away from it for everything we do, just about. Well, how do I rewrite this? It's not x to the 2/3. Yeah, power on top because it's powerful, roots on the bottom like plants. And the reason I make a big point of that is some of us still write it the wrong way, and then all your derivatives are wrong. That sucks. And of course, this would just be what?
1/2.
Yeah, 1/2. So just make sure you rewrite the function correctly, so your derivatives don't get all freaky. Do it. So that's number 2 on the back of that sheet from last time. It's got that function on it. Let me know if you don't have that sheet.